Yeah, good morning, students. So, today we'll be looking at our next topic of discussion, which is nothing but bipolar transistors. Okay, so over here in the picture shown below, we have the rather simplified diagrams of basically there are two types of transistors. One is the NPN transistor that is shown over here, and the PNP. Okay, so what is happening in bipolar transistors is nothing but okay, so you take a semiconductor of one type, that is if it is NPN transistors. Okay, so you are taking a P type transistor and you are basically sandwiching it between two N type regions. Okay, sorry, you are taking a P type semiconductor and you are basically sandwiching it between two N type semiconductors, so that forms an NPN transistor. Okay, similarly, what is PNP is nothing but you basically take a N type semiconductor over here and you basically sandwich it between two P type semiconductors, so that becomes a PNP transistor. Okay, so there are three terminals in this bipolar transistors. Okay, so the first terminal is called the emitter, the middle one is called the base, B for base, E for emitter, and the last one is called the collector. Okay, right, so this is the symbol of the transistor. So the electrical symbol is something like this. Okay, so this is the symbol. Okay, so the middle one is the base, the one with the arrow is always the emitter. Okay, and the other one is your collector. Okay, so this is the symbol of NPN transistor. Okay, so this is how a PNP would look like. Okay, this is the base. Okay, so the emitter would rather have the arrow inwards here. Okay, and then this is the collector. So this is the symbol of PNP transistor. Okay, so the same has been depicted here as well. Okay, so but there is one other thing to take care of, or one important thing to take care of here. See, the NPN bipolar transistor contains a thin P region. Okay, between two N regions. We have seen that the P region has been sandwiched between two N regions, but what it also is, it is also a very thin region. Okay, very thin region physically. Okay, so I would rather put it this way. Okay, so this is how it might be. Okay, so this is a very rather thin region, that is the base region is of the transistor of a NPN or a PNP bipolar transistor is very thin compared to the emitter and collector regions. Okay, so these two are our emitter and collector regions. So compared to these two, the base region is very thin. Okay, so proceeding further. Okay, so I have taken the NPN transistor for our discussion today. Okay, so our topic of discussion would be NPN transistor. So like the structure indicates, okay, so there are basically uh, N, P and N regions, although I told you that P region is very thin. Okay, just to be able to draw diagrams properly, I am depicting in this fashion, but you know that the base region is very thin. Okay, so now let us see how many PN junctions are possible here. Okay, so because this is one N and P region, one PN junction is possible over here, and because this is one P and N type region, another PN junction is possible over here. Okay, so any PNP or NPN transistor has basically two PN junctions, and if it is two PN junction, okay, so each PN junction is capable of either being in reverse bias or forward bias. Now since there are two junctions, okay, because we have two junctions, one is between these two and the other is between these two, okay, so four possible bias combinations are possible, okay. So that is both the junctions being reverse bias, one is reverse bias, the other is forward bias, one is forward bias, the other is reverse biased, and both forward biased. I think you know from DLP this corresponds to 00011011. Okay, so because we have two junctions here, four possible bias combinations are there in any given bipolar transistor. Okay, right. But what is our bias combination of interest? Okay, the bias combination of our interest is this one, or rather let me be very specific. Okay, so the major application of transistor is it is used as an amplifying device, that is shown here. Okay, so if you want to use it as an amplifying device, okay, the base emitter junction should be forward biased and the base collector junction should be reverse biased. Okay, so let me explain it. Okay, so there are two junctions. Now we have seen this is NPN. Okay, so we have named this the emitter, the middle one the base, okay, and the third one the collector. Okay, so this is first PN junction. Okay, and this is formed between the emitter and base terminals. Okay, so the first junction is called B junction. Okay, so it is always spelled as the P terminal first followed by N terminal. Here P terminal is base, so that is why this is called BE junction. Okay, similarly over here the second junction is BC junction. Okay, so here also it should be spelled as P terminal first followed by N terminal. So here P terminal happens to be base and N terminal is collector. So this is second junction we have is BC junction. Okay, so if you what is the um, uh, uh, what is our bias combination of interest? Okay, so we want the transistor to be acting as an amplifying device, and if it needs to be an amplifying device, okay, what is the condition? The base emitter junction should be in forward biased and the base collector junction should be in reverse bias. So this is the possible bias we are looking at. Okay, we wouldn't be discussing other bias conditions in this lecture, so we'll be solely looking at this particular bias condition. Okay, so there are four possible. Out of these four we are looking at this one. Okay, right. See here the P type is connected to ground. Okay, and the N type or the base is connected to ground, and the emitter through this resistor is connected to some negative potential. So this PN junction is forward bias. Similarly, if you see this PN junction, this P type, this P side is connected to ground, that is say 0, and N type is connected to a positive battery terminal, that is N is at a higher potential. So BC junction is reverse bias. So basically this is what we are trying to decode in this. This is what rather we are trying to understand in this video. Okay, so let us proceed now. Okay, so right now what do we have? We have two junctions, and one of them is forward biased and the other is reverse biased. Let's see how they behave if we put them together. Okay, so this is an N region, this is a P region, this is an N region. So what is happening? We know that the emitter base junction is forward biased. Okay, so because the emitter base junction is forward biased, okay, and one more thing that we should keep in mind is the base region is very thin. Okay, so the base region is very thin, remember. Okay, right. Right, now what happens is since this junction is forward biased, okay, what would happen? There would be uh, basically a current flow from P side to N side. Okay, isn't it? We all know that. Okay, so from P to N there will be current flow in this fashion, but we will also look at the individual majority carriers. Okay, so let me blow this up. I am showing you only the N and P type region. Okay, so only this junction I am trying to show here. Okay, so this is my emitter and this is my base. Okay, see what is happening here. So the majority carriers we know from the operation of the diode, the majority carriers in the p side are holes, so they diffuse through the junction to the n side. Okay, the majority carriers here in n side are electrons and they diffuse from the n type region into the p type region, but the net effect of current flow is is always the direction of holes. So that is why we get a current from p to n, that is out of the emitter region. So I think we all know this from our basic PN junction understanding of PN junction diode. But what is even more interesting here is, okay, see here the physically this emitter is large. Okay, so physically emitter is large compared to your base. So what that results in is the number of electrons. Okay, so the emitter current, I am drawing an important conclusion here. See, though the emitter current here is rather very much dependent on the electrons that are diffusing from n type region to the p type region rather than the holes that are coming from the base, because you see here n type region is much more wider, it has more area compared to the p type region. So what happens is the number of holes that are diffusing from the p type region to the n type region will be lesser compared to the number of electrons that are diffusing from the n type to p type region. Okay, so your emitter current maximum portion of your emitter current is because of the electrons that are diffusing from the n type region to the p type region. I think because that happens because of the sizes over here, because n type is fairly large over here and p type, like we have discussed earlier, p type base region here would be very very thin. Okay, right, so the majority portion of IE is composed of the electrons that are diffusing from n type to the p type region. So have that in mind, we'll revisit that. Okay, right, now we know that this base is a p region, so what would happen to the electrons that enter this p region? Okay, so let us discuss. Now the second junction also comes into picture. Okay, right, so let me draw the other junction as well. Okay, so this is my PN. Okay, so I am drawing the base collector. I am looking at base and collector terminals over here. Okay, right, so what is this base region now being what is this base region experiencing now? It is experiencing an injection of negative charge carriers or electrons, right? So the base is getting electrons from the emitter region, right? Now because this is a p type material base, okay, these electrons should start recombining, but from our understanding of PN junction diode, we have seen that in a PN junction diode, okay, so the electrons that come into the p type of region, okay, so they start diffusing, okay, and they become the minority carriers in the p side, and their influence is limited only to the vicinity, if you remember. Okay, so in forward bias, especially in forward bias, we have seen that the current flows from p to n because of diffusion. Okay, and we have also concluded that near to the vicinity of the junction, I should rather say junction here, near to the vicinity of the junction, okay, the current flow is due to diffusion, but further near away from the junction, we know that the current flow is due to the majority carriers. Okay, why? Because all these minority carriers that have been injected from the other type, they recombine because there are majority of holes over here. Okay, we know that the current flow due to these electrons that have crossed over into the p region is predominant at the vicinity of the junction. We have discussed that in detail in our first session. Okay, right, so the same would be happening here. The electrons from emitter, okay, so here the electrons are coming from the emitter region, recombine with the holes in the base by the time they reach the edge of the BC junction. Okay, so that is what our common understanding of an PN junction type diode is. And there wouldn't be any electrons left. But is that the case here? Thus, that is not the case here, because the base has been made a very narrow region. Okay, so that is what I have been telling you since the start of this lecture. The base is a very, very narrow region. Okay, so NPN. Okay, so electrons are injected from this n type emitter into the base. Okay, but what is happening here, because the base is so thin, before these electrons are completely recombined in the base region, okay, so they reach the vicinity of the second junction. Okay, now what is happening, the electrons are coming from the emitter. Usually if it is a PN junction diode, they are supposed to completely recombine within the vicinity of this junction. But what is happening here, because the p type base is very, very narrow. Okay, the p type base is very narrow. Okay, what is happening, the electrons are not completely recombined in the base region. The electrons that are injected from emitter are not completely recombined in the base region, rather they reach the edge of the other junction. Okay, so here one very important phenomenon takes place, so please pay attention and listen. Okay, so at the second junction, what is happening is, because the second junction is your base collector junction. Okay, so NPN. Okay, remember this has to be very thin, this is very thin. Okay, so remember this is your base collector junction, and base collector junction is of course reverse biased. Okay, so we are looking at the condition in which base emitter junction is forward biased and base collector junction is reverse biased, remember. Okay, so now because it is reverse biased, okay, so what happens, there will be depletion region in this fashion, and of course on the p side we have negative acceptor ions, and on the n side we have positive acceptor ions. And these we know from PN junction diode behavior that these ions form the depletion region. Okay, and once I say depletion region, what should come to your mind? Okay, okay, because depletion region consists of immobile ions. Okay, so what should immediately come to your mind? Electric field. Okay, so here we have a good electric field from the n type to the p type, or from the positive ions to the negative ions. Okay, now what is happening here? Okay, so there are electrons that are being injected from emitter into the base, very thin base region. Okay, and these, because this is very thin, okay, the electrons are not completely recombined in the base. Okay, before they reach the edge of the base, they are not completely recombined, but as they are reaching the other junction, as they are moving towards the other junction, what do the electrons experience? The electron experience a very strong favorable electric field. Okay, this electric field now starts pulling these electrons. Okay, so it is a very favorable electric field. Okay, so even though this junction is reverse biased, okay, what happens to the electrons that are injected externally? Okay, so these are now pulled across the junction. Okay, so these electrons pull through the junction and they move to the collector region. Okay, see how beautiful it is. Okay, so what is happening here, okay, from the textbook is, the ability of a reverse biased PN junction to effectively collect externally injected electrons. See how beautiful the language is in this textbook. Okay, so what is happening in the collector? The collector, even though it is reverse biased junction, what it is doing, it is efficiently collecting externally injected electrons. Okay, so the PN junction the current that is conducting in the PN junction is not due to the electrons in this n-type region. No. What does this line say? So the ability of reverse biased PN junction to efficiently collect externally injected electrons. So the externally injected electrons are in fact injected from the emitter region, which are pushed through the base, okay, which are rather pushed through the base, okay. So externally injected electrons proves essential to the operation of bipolar transistor. So this one line is a beautiful line from the Donald Neiman textbook, okay. So this summarizes the transistor action in this bias condition, okay. And this is very important for our understanding too, for understanding the transistor action. So this line efficiently summarizes, okay, your transistor operation. A beautiful line from a beautiful textbook, right? So we'll proceed further. Now let us try to understand, okay, right? I have forgot to mention. So if your emitter base or base emitter junction is forward biased and base collector junction is reverse biased, okay, so that means the BJT or the transistor is said to be in active region. I forgot to mention it previously, okay. It is almost also called as forward active region by some textbooks, okay. But active means that emitter base junction is forward biased and base collector junction is reverse biased, okay. So when somebody says BJT is in forward active region, so they are referring to the bias condition, that is base emitter being forward biased and collector base or base collector being reverse biased, okay. Right, now let us study the currents in this transistor in the active region.